In this problem, we are given the following diagram here. It is of an inductor. We are told that the current in the inductor is 10 times the cosine, with our omega being 10,000 times t plus an angle of 30 degrees. We are also told that our inductor is 20 millihenries. We are to calculate the inductance reactance and also the impedance of our inductor. Then we need to calculate the phasor voltage and then write a steady state equation for it. So I'm going to solve A and B together, where we need to calculate the reactance and impedance of our inductor. This is going to be a very similar formula. The base of it is going to be that our x of L is equal to our omega times our inductance. For our z of L, it's going to be almost the same thing, except for impedance, and very important, the reason why we're going to modify this is that we have a j out front. So it's going to be j times our omega times our L. Now, this isn't very important for this problem specifically, but if we were to look back at a previous problem we did with the capacitor, it is super important because we are going to have a negative after we flip this J and the bottom to the top, and it will change our Z for capacitance. But our Z for inductance is just the same or very similar to our inductant reactance. So knowing that the only difference is going to be J for our Z, we can multiply these out. We know that our omega is 10,000 and that our inductance is 20 with a milli, and a milli is 10 to the negative cubed. So we're just going to have this in here. And this will give us 200 for our x of L and a j200 for our z of L. But our j is already written in our z of L outside, so we're not going to put that in the answer. It's just important to know that that accompanies it when we find impedance. Now we need to calculate the phasor voltage for our V. We are calculating voltage, so we know that this is going to be our current times resistance, or impedance. We're going to say resistance here, but we really mean any form of impedance. We know that the current is given to us up here, so we are going to take this formula and set it equal to a 10 with an angle of 30 degrees. This is our phasor. And we don't need to convert it because it's already in cosine, and we're going to be solving it for cosine. So knowing this, we're going to plug this in. Our current is 10 with an angle of 30 degrees, and we know our resistance is this Z of L, and our current is the current given to us. And our Z of L we found to be a J of 200. Now, since these are two different things, our J of 200 is in rectangular form, and our 10 angle 30 is in polar form, we can't just multiply them together. We need to make one of them the other, and the easiest one to do is make the first part, the 10 with angle 30, a rectangular form. To do this, we are going to take our number, which is 10, and multiply it by a parenthesis, and then inside of our parenthesis we're going to have cosine times our angle plus j times the sine of our angle. In doing this, we're going to get approximately 9 plus j times 5. And then we're multiplying all this by j of 200. And this is going to give us approximately j times 1732 minus 1000. Remember, we're factoring this into here, so it's important to note where the j goes and what it does to our problem. And this is going to be the rectangular form for our phasor voltage. Now we need to find the polar form for it because it asks us to do that in the question. We want to graph this first to make sure we find the correct angle. So we know our x is our real number and our y is our imaginary number. X is negative, so it'll be over here. Our imaginary number is positive, so it'll be up here. That means our angle has to be somewhere inside of our second quadrant. Now we are going to convert this from rectangular to polar, and to convert this, that our v of max is equal to the square root of our real number squared plus our imaginary number squared. And our angle is going to be equal to the tangent -1 of our imaginary number divided by our real number. And plugging that into the formula, we are going to get 2000 with an angle of -60. It's important to note that our angle is not in our second quadrant. In fact, it's in the opposite quadrant, quadrant 4. So we're going to have to add 180 to this to make it in quadrant 2. And then we will have the right angle. Now, this is not the correct number either for our magnitude. And it's because we are given our initial current in milliamps, and our equation does not want it in millivolts, it just wants it in volts. So we're going to have to convert this from a milli, because currently it is in milli, to just amps. So we're going to take our 2000, which is currently again in milliamps, and multiply it by 10 to the negative cubed, and that will cancel out the millis, and we're just going to be left with amps. If we do this, we're going to move the decimal place, which is over here, over 3 spots, and that's just going to leave us with a 2. So our final answer is going to be 2 with an angle of 120 degrees. And if I reveal the answers, we can see that is what we need for part C. For part D, it's just plugging in everything that we know. We need to write a steady-state expression, and our omega is this 10,000, so that means our omega is going to be this 10,000 here. We know that our magnitude is 2, so we're going to plug this into here. That is the magnitude, or V max, and our angle we know to be 120 degrees, so we're just going to plug it in for this last spot. That is how you would go about solving for this problem. If you want more network analysis problems, there's a playlist in the description, and if you want notes that go over this topic, they will also be in the description below the like button.